Welcome to SRA 221. In this lecture, we will be discussing password entropy. As we have discussed previously, one of the most common forms of authentication is password-based authentication. So how do we know that a password is actually strong enough? There is a way of measuring the effectiveness of a password and resisting guessing attacks, which is referred to as entropy. Entropy essentially determines how difficult it is to guess a password. Assuming that the attacker does not already have the password, and it calculates how much effort would need to be put into cracking the password being used by someone. The strength of the password is determined by looking at its length, complexity, and unpredictability. There are two types of entropies: guess entropy and min entropy. Guessing entropy is an estimate of the average amount of work that is required to get any of the passwords of a given user. The min entropy is the measure of the difficulty of guessing the single easiest password in a given password population. Essentially, it is determining how long it takes and how difficult it is for an attacker to gain the password of a victim using available possible passwords. Password entropy is computed by considering the length of a password and a digitized form. If a password has k bits, and the bits are chosen at random, then we know that there are 2 to the power of k possible passwords, and therefore we say that the password has k bits of entropy. So if a password length of L characters is chosen at random from an alphabet of B characters, the entropy of the password is B sub L. Now let's take a look at an example. Suppose you have a password length of 8 and an alphabet of 94 characters, which is typically the number of characters available on your keyboard. The entropy here would be 94 sub 8, which equals 2 sub 52. In other words, the password has 52 bits of entropy. Estimated password entropy is based on the work by Claude Shannon on entropy of English words. It's harder to predict the first letter of an English text, but given the first letter, it is much easier to guess the second, and given the first 2, the third is easier still, and so on. Shannon estimated the entropy of the first symbol at 4.6 to 4.7 bits. Declining to about 1.5 bits after 8 characters. The logic or assumptions to calculate entropy in Table A.1 are as follows. Number 1, passwords are subject to dictionary tests. Number 2, composition rules, lowercase letters, uppercase letters, and non-alphabetic symbols. Number 3, 94 characters from keyboard. Number 4, the entropy of the first character is 4 bits. Number 5, the entropy of the next 7 characters are 2 bits per character. Number 6, for the 9th through the 20th character, the entropy is 1.5 bits per character. Number 7, for characters 21 and above, the entropy is 1 bit per character. And number 8, a bonus of 6 bits of entropy is assigned for a composition rule that requires both uppercase and non-alphabetic characters.